Hello everyone, I am Nuwan, Attygalle. So today I am presenting comparative testing of radar signal presentations when sensing through materials. Okay, now how do I go from here to there? So we are very interested in gestures. Why gestures? So when we communicate with each other, we use gestures a lot here. And also when we communicate, we tend to move our hands hands a lot. And these gestures are coming as an integral part of the communication, like human-to-human communication. Even babies use gestures. Even before they use their very first words, they use gestures. So gestures are very innate to our language. So when we communicate with computers, most of the time we rely on the keyboard or the mouse to give commands and interact with computers. Yeah. So, but when we interact with humans, we tend to speak, we tend to greet each other, we tend to gesture a lot. So then these gestures are very close to human communication. So even though the gestures is one modality that we communicate with computers as well. Nowadays, the computers has the feasibility of recognizing gestures. So here, in our study, we would like to use gestures in challenging situations to communicate with gestures. So specifically, the problem that we are trying to address is sensing through materials. So let me give you an example. Yeah. So now let's say suddenly I get a call. So my phone starts ringing and my phone is in my, actually I really got a message, but anyway. So my phone is in my pocket and now it starts ringing. So the question is, how do I silence the phone? So I take out my phone and then press the button to silent and then put it back. Yeah. What if I could silence my phone without taking it out? So if the phone has a radar sensor, then I could sense a gesture like swipe left, and then it would sense my intent, and then it would I can silence the phone without taking out the phone. But in that case, the phone embedded radar sensor has to sense my intent through the material of my trouser, yeah, or through the material of the pocket. So the radar waves has to go through the material and bounce off from my hand and again through the material to the radar sensor. So when these electromagnetic waves penetrates through materials, it can be distorted because of the refractions or diffractions. Because of this, the radar signal can be differentiate, yeah, so can be diffracted. So this question, we are trying to identify this, what are the challenges of sensing through materials and how to mitigate these material problems. Okay. So when classifying gestures or for any classification problem, what we do is we get the data. So this is a gesture classification problem. So nowadays we have several machine learning architectures, some 1,000 machine learning networks, network architectures. So in order to identify something or for a classification problem, we can get the data. So once we have the data, we can train a model on that data, and then we could do a classification. This is very straightforward. So once you have the data, you can do most of the classification part. Yeah. The main thing is you get the data. But here, this radar signal is more abstract signal. Even though we get the data, we can throw the data into a deep learning network. But if we have meaningful data, let's say rather than having all the raw voltages of the radar antennas, we can get the range of the target that is moving, or we can get the relative permittivity of the interface of the surface. So these are meaningful features rather than the voltages of the antenna. Or we can get the XYZ coordinates, the Cartesian coordinates of the moving target. So this is very meaningful. So if we can have access to such features. So basically, this the radar signal is we can extract features from the radar signal, mainly in the time domain, because in the time domain we have amplitude and the phase changes of the radar signal. And also when we convert it to frequency domain, then we can have the range Doppler images, range angle or angle Doppler images. And also we can combine time and frequency domains together, so we can have some spectrograms like range and spectrograms, wavelet transforms. We can apply wavelet transformation and then create some time frequency representations. And also we can have micro Doppler representation. So all are these, not just the raw data, but a little bit advanced feature extraction. So then once we extract features, we have meaningful data. So with the meaningful data, we can implement a simple classifier. So now all the classification is not up to the model, it's not up to the deep learning model, but we know what's going on inside the model and we are fine-tuning the model. So this also can be, the model can be lightweighted as well. Okay, so mainly here we have, range Doppler images. In the range Doppler images, in this axis we have the range of the target that is moving, and this is the velocity. And also we have range angle. So here, this is the angle and this is the range that is the moving target of the moving target. And we can have some point cloud data. So this is actually XYZ. This is like Cartesian coordinates of the trajectory that is the hand is moving. And also we can have spectrograms. So these are some few examples of data representation methods. So apart from this, we can have micro Doppler images as well. And also there are several data representation methods as well. What we wanted to do is, okay, I have to find mine. What we wanted to do is, now we have several data representation methods. But then the question is, which one to use for sensing through materials? Okay, our experiment, it's like this. So we have our sensor here. So I will just briefly explain the experiment setup. So we have our radar sensor here, and we are performing our gesture here. So this is the, yeah. So here's the sensor plane, and this is the gesture plane. In between this, we put several materials. So in this case, we put 14 different materials. So we are sensing all the gestures through the material. Once the radar signal goes through the material, it gets distorted. So basically, according to the, so the main challenge is to differentiate the interested signal from the noise. So when we have materials in between, it's very hard to differentiate the actual signal from the noise. So this is the problem. With the radar equation, if the signal to noise ratio is higher, the signal is better. So we have a much higher probability of distinguish noise from the signal. But by introducing materials, we actually increase the loss component of the radar equation. So this is the problem of now. This is why this increasing of the loss component is the reason for not being able to distinguish the noise from the signal. But what we can do is, when we are pre-processing the signal, we can have several methods to improve this signal to noise ratio. Rather than getting the raw signal, we can put data representation methods to increase the signal to noise ratio. Now, here, what we are going to do is, we are going to compare different signal representation methods with the accuracy. So if we train with range Doppler images, what would be the accuracy? If we use micro Doppler images, what would be the accuracy? If we use range angle images, what would be the accuracy? So this is what we are going to do. So how to test the system? So first we get the data. So in order to get the data, we are we are following this. Yeah, when we are training the data, when we are training the model, we get the data in no material condition. So you have the sensor here. Between the sensor and the gesture, you don't have any material, and we get the data. So we use this condition to train our models. So when testing the model, we introduce this. So we have our sensor here and the material here, and we have the gesture plane here. So we train our model with this setup, and we test the same model that trained without any material with material data. And our data capturing setup, it's so for data capturing, we use Texas Instruments sensor with 4 transmitters and 3 transmitters and 4 receivers. And we use a leap motion sensor to have access to the real data. So we have, with the leap motion, it captures the hand coordinates. And here we put several materials, and then we perform the gesture here. And also we capture data without any materials as well. Now I will hand over the slides to Una to describe the gesture set that we are going to do.
Okay, hello. I'm going to briefly explain how we did the data capturing. So to capture the data, we did it with 20 participants who all performed gestures over of 24 gestures with 5 repetitions. These gestures are found in the literature, and they're called micro gestures as they're performed just with the hand, not with the whole arm. And all of the participants did 5 repetitions of those gestures over 15 material conditions. As Nuwan said, there were 14 material conditions, so 14 materials which participants performed on, and 1 no material conditions, which was used to actually train the data. So all of this led to the data set of 40,000 gesture repetitions. On the right, we can see the picture with the actual the names of the gestures and how they were performed. So first picture is always the starting position, and the last one is ending position. And if you can see the black square in the middle, that's the position of the sensor. So you can orient it maybe a bit better. So thank you. I'll hand over back to Nuwan now.
Okay, thank you very much, Una. So this is the gestures that we captured. So after capturing, we trained a convolutional 3D based network architecture. So we only tested one network architecture, varying with different hyperparameters. So we tuned the hyperparameters matching, to get the best performance for each signal representations. So basically, we trained a convolutional deep learning network based on convolutional 3D layers with IQ signal as the input, and we so IQ signal with the radar data cube. Yeah. So with the radar data cube, so IQ signal is one data input, and then we did IQ signal with FFT along the dimensions. Like you have the range dimension, and you have the spatial dimensions, which is the antennas, and and also the third dimension is the slow time dimension. So we just perform FFTs across these dimensions, and we got another data representations with IQ signal with FFT applied, and also we tested with range angle images and also Range-Doppler images. So we trained the models without material condition, and we tested the model with material condition. So once we are testing, and after, so we have 14 different materials, and now when we test against the materials, we have 14 accuracies. Yeah, for for a model that trained with IQ signal, when we test with when we are testing the model with the material condition, we have 14 performances, one for each material. So now we have 14 accuracies for IQ, we have 14 accuracies for this, we have 14 accuracies for range angles. Now we are going to, then we performed a significance test to see which signal representation is better or worse, to see whether there's a significant difference between. And then we found out that there's a significant difference between IQ and IQ wave 50, and also range angles and range angles. And here you can see how each signal representations performs when it's on the material condition. And the limitations of, as I mentioned earlier, we only evaluated against one network architecture based on convolutional 3D. And also, so far, we only tested 4 different signal representations. And we actually did for kernel, we actually experimented with point clouds, but we couldn't get a good baseline classifier. Basically, the point cloud data didn't work well for no material condition. So among the attendees, we have expertise in, experts in generating point cloud data. So maybe we can collaborate. If you are very interested, we are very happy to do a collaboration. So, and also for the training set, we had very limited training set. Even though we have 24 gestures, for one gesture, we only had around 70 gesture repetitions for training. So this is quite low. This is one of the limitations. And also we found out that Range-Doppler and Range-Angle data representations are better than just the raw data. So for the future, we would like to evaluate, as I said earlier, we would like to evaluate more data representation methods, such as point clouds or micro Doppler images and also we would like to test the signal representation against different radars and radar configuration. And also we would like to do Bayesian influenced forward or inverse modeling to tune the signal, actually to improve the signal based on the radar equation. So that's all. Yeah, that's all. And thank you very much. So if you have any questions, I'm very happy to